Hey everyone, it's David with Streaming Relativity, home of the Astro N.I.N.A Observatory. The Rosette Nebula. What a beautiful deep sky object. It's located in the constellation of Monoceros. And not only is this a beautiful target, it's really easy to image by amateur astronomers. And it's a wonderful example of an emission nebula with several very strong hydrogen alpha regions. And it even has an open cluster at its center. So I took this image on the 26th of February in 2024 using my Astro Tech 115 EDT refractor and the ASI 2600 mm Pro camera. So in this video today, I'm going to quickly go over four things. One, how do you locate the Rosette Nebula and image this amazing target? I'll talk about the range of equipment and setup configuration that's needed to capture this successfully. And then we'll do a quick tour of its features. And for those that are interested, I'll do a high-level kind of overview of the Pixinsight processing workflow. And if you like this type of content, please subscribe. I produce videos every week, and there's a cool community forming here on the channel, and I'd love to have your support. And with that, let's check out the Rosette Nebula. Okay, let's begin by finding the Rosette Nebula, and I mentioned that it is in the constellation of Monoceros. Now, Monoceros is a difficult constellation to locate on its own, so I recommend that you use Orion and the Betelgeuse star, which is Orion's right shoulder, left on this image as we're looking at it, but his right shoulder, it's the brightest star that you'll see. And just to the east, you're going to find the snout of Monoceros, which is where the Rosette Nebula is located. Now, it is visible to northern hemisphere astronomers as well as southern hemisphere astronomers. If you want to orient yourself to this target when you're outside, perhaps the easiest way to do this is to look due south and then begin to move your vision up towards the zenith, which is directly above your head. Just past that halfway mark, you'll be able to spot Betelgeuse, and this will give you a general idea of where the Rosette Nebula is. Note that I set my planetarium software to the date and time that I began shooting the image. So this is everything here is relative to that date and time and my location on the globe. Okay. So other things to note: it is below the ecliptic. This is the path that the planets and the moon seem to travel, and it is just above the celestial equator, which is the line that connects east and due west. Okay, so hopefully this will give you guys a good sense of where you can locate the Rosette Nebula. Now, it is not visible to the naked eye, as in fact, most of the stars in Monoceros are quite dim, and that's another reason why it's a difficult constellation to find by eye. But as we zoom in here, you'll note that this field of view matches the combination of my telescope, my image sensor, and the focal reducer that I have. So this is a focal length of about 644 millimeters. So, and you can see that the Rosette Nebula, this glorious emission nebula, pretty much completely fills the frame, and theoretically, it extends beyond the boundaries of this frame. So this is a very rich image that we've captured here. Okay, let's get into the details of how I'm set up. Okay, February 26th was a beautiful, beautiful evening. As you can see here, this is prior to sunset and twilight. The Astro N.I.N.A Observatory, which is, by the way, a rescued observatory, and so pleased that several years ago I was able to pick this dome up and invest the time I needed to get it set up on the back of my property. At any rate, I'm gonna quickly go over for you how I configured my session here, and So first thing, again, I use Stellarium. So on screen we see Stellarium, and what I've done is I brought the Rosette Nebula into focus, and once I have that target acquired, I am able to analyze what the session should look like. I started shooting around 7:30, which is about a half hour before it was going to cross the meridian. And then if you'll note that once it crosses meridian, 1, 2, 3, let's call it 4 hours of, uh, of, of accessible imaging time before it starts to sink into the western horizon. So if we maybe get a better look at that by changing our view in Stellarium, the target will eventually begin to sink into the west. Okay, with that, let's take a look at what the sequence itself looks like in N.I.N.A. Very straightforward. Once you get your target in your planetarium software, you can pull it in for framing, which I did, and then you can add that target to your sequencer. And in this case, it's a deep sky object instruction set, and simple slew and center to the target. When this runs, the very first step it'll do is to slew and center. And I chose to image 60 30-second exposures with my IR UV cut filter or my luminance filter, gain of 0, offset of 50. I find that to be the best setting for broadband. And then I did each of the narrowband filters at a gain of 100, offset of 50, 2-minute exposures, and I did 60 frames of hydrogen alpha because this is a hydrogen alpha rich target, and I did 30 frames each of my sulfur and oxygen. And so in total, if we add this up, we're looking at 1 hour, 2 hours, 4 hours, 4.5 hours worth of data. And that is all you really need on this target to capture an image that tells a wonderful story. One last thing I'll point out: as I mentioned, I used my EDT 115 telescope for this, but this is an excellent target for 80 millimeter telescopes, and which are very common, very inexpensive. And if you own one and you have a decent mount for it, you can image this target and get a wonderful composition of this target. So I encourage you to go out there and try it. So with that, let's go ahead and tour the image. Okay, so let's start with the broadband data, which I captured with an IR UV cut filter. Now, these filters are inexpensive, and they're used to block the infrared and the ultraviolet wavelengths from hitting your sensor, and that just leaves the visible light only. And so ultimately, it's the intent here is to improve contrast by limiting the bandwidth of photons that are hitting your sensor. Think of the UV filter as a high-pass filter that allows wavelengths only above 400 nanometers to hit your sensor. And then think of the infrared filter, the IR filter, as a low-pass filter that allows wavelengths only below 700 nanometers to hit your sensor. So the combination produces a filter that only receives photons between 400 and 700 nanometers. That's the visible spectrum. And within that broadband, we see stars and faint nebula regions. And this is the view, I show this because this is the view that early astronomers saw. And if we put an overlay on top of that, we see a bunch of NGC designations. And those correspond to what the 19th century astronomers saw with their telescopes. And our view today is consolidated. We simply refer to the broader Rosette Nebula as NGC 2237, which again is the entire nebula region. And then we have NGC 2244, which is the central open cluster, star cluster, which is a stellar nursery that's actually powering all of the emissions in this region. But clearly, this data alone, this broadband data alone, is insufficient to produce our beautiful color photograph. To get that photograph, we need to reveal the finer structure and depth in the emission nebula regions, and we have to use narrowband filters for that purpose. So let's start. Let's look at what we have here, which is the hydrogen alpha data, and what an incredible difference this filter makes. The hydrogen alpha filter narrows the wavelength to a very small band centered around 656 nanometers, which is the wavelength that hydrogen emits, hydrogen alpha emits through a vacuum. And so by isolating to this narrow band, we get a tremendous amount of contrast within the structure, and it really stands out. Look at how the dark lanes and the nebulous region, contrast each other, and this is just wonderful. I could study emission nebulas and hydrogen alpha alone and always be amazed. So again, this is roughly 2 hours of hydrogen alpha data. Let's take a look at the O3 data. This is emission from oxygen, doubly ionized oxygen, in fact, and this filter here will narrow the band to roughly centered around 500 nanometers. So it's on the opposite end of the spectrum from hydrogen alpha, and we can see here that the signal is strongest in the inner ring of the structure. And finally, we could take a look at the sulfur, which is a sulfur, an S2 filter will narrow the wavelengths centered around 672 nanometers. And notice that the S2 signal in this case is strongest in the outer ring. So these different areas of strength for these different filters will help you appreciate the final colorized image. But before we jump at that colorized image, I really want to make sure that everybody's clear that an emission nebula is caused by the excitation and then the recombination of electrons and the nuclei of these three different elements. And the atoms, when they're recombining, they emit photons in these specific wavelengths. Now, emission nebulas are very different than reflection nebulas, and reflection nebulas are typically captured with broadband filters, visible light filters, wide spectrum, because they really are caused by light being scattered from dust. So there's some light source, star, that is emitting its own light, and then that light is bouncing around in the dust particles, and so we capture that using a broadband set of filters. And we'll cover reflection nebulas in a future video. So let's pull this together, this data together, into a colorized visualization, and I just think this is a stunning image. And I'm a huge fan of the show palette, which of course was popularized by the Hubble telescope. And the show palette is taking the sulfur signal and assigning that a color of red, taking the hydrogen signal and assigning that color green, and then taking the oxygen signal and assigning that a color of blue, and then combining those into an RGB image, and voila. This is just 4.5 hours worth of data. If you scour the internet, Astroband and other sources, you'll see people that have, 10s, 20, 30 hours of data on this subject, and you can get to some very beautiful representations of this deep sky object. But having said that, with just 4.5 hours of data, I think we've got something incredible. In fact, I printed this, and it looks good. This thing looks really good, even up to 15 by 10 prints. So let's take this image in and a few cool facts about the Rosette Nebula. The nebula itself is about 5,000 light years away from Earth, and it is huge. It's about 150 light years in diameter. So this makes it one of the largest deep sky objects in the sky, and it is an awesome target for wide field instruments, which are typically lower cost instruments, and so it's really accessible. And having said that, it's also a great target for more advanced astrophotographers who are using longer focal lengths, who perhaps want to study very specific areas within the object itself. And let's not overlook the beautiful open cluster, which is powering. It's just a stellar nursery that's powering all these emissions. That's our NGC 2244, and there are about 2,500 stars forming in this region, and it's just a remarkable image. And it also has a very unique history. As I mentioned, it was discovered in part. So, for those who are old school and want to study some of these NGC catalog items, you can with longer focal lengths. You can zoom into those specific areas and get tremendous detail. Finally, there's such an abundance of data here, narrowband data. You can choose any color palette you like to represent this. I like show, but there are so many other ways. You're only limited by your own creativity, and that is it. So please play around with this, and this is just such a gorgeous object, so very accessible, and I highly encourage all of you to get out there with your telescopes and do some imaging. All right, with that, let's talk a little bit very briefly about how I processed this with Pixinsight. Okay, I'm a big fan of relatively simple workflows for my image processing, and of course I do all my stacking in serial, so you have to start with your stacks of your data. In my case, my IR UV cut filter data, my broadband data, as well as my hydrogen alpha, my sulfur, and my oxygen data. Pulling those stacks into Pixinsight, we do a star align, dynamic crop, and a basic histogram stretch. This is all prep work, and I'm sure you're all familiar with this. If anybody's interested in me doing a deep dive on any of those steps, I'm happy to do it. Okay, I then use pixel math, and when I say I am a kind of purist when it comes to the show palette, I am a purist. So literally, I'm going to assign sulfur to red, I'm going to assign hydrogen to green, and I'm going to assign oxygen to blue. And the resulting image is the colors are pretty much where I want them to be. Of course, it's dull, it's not balanced, it's going to need some additional stretching, some curves work. But before I do that, I generally like to go to a starless image. So I'll separate the stars from the composed image, so that I have the nebula in one file and the stars in another. Now I happen to do that for both the composed RGB image, but I also take the stars out of the my luminance frame, my IR UV cut filter data, because I'm going to combine those stars back with the image, and use them as opposed to the stars that are clearly a little bit tainted in the violet in the violet zone. Okay, so on the starless image we do curves transformation, and I usually do a little bit of noise and blur reduction here as well. And now we have what I like in terms of colorized version of the nebula. Now there is a step here. There's a new process that is available in Pixinsight. It's a narrowband normalization. You can Google that, search on YouTube for it, or if anybody wants me to do a deep dive in this, I would be happy to do it. But basically what this will do is try and give you a normalized rendition of your image based on the palette that you composed it under. So I composed under show. Running that normalization produces a very interesting alternative to my original show palette. Again, this is a matter of preference and which one you like, but either way, our final step here is to recombine the star data with these, and I'll do that for both to show you what each looks like. So when we recombine the stars from my IR UV data, this is what the show palette looks like, and the same for the normalized version of it. Both really interesting, and in fact, as I was doing this video, I kind of like something in between, so I took them into GIMP, and I just did a 50-50 blend of the two, and here's a final image. So that's my processing. Again, if anybody's interested in me doing a deeper dive into any of these steps, just let me know in the comments below. I'd be happy to do tutorials on those. Okay, that's a wrap, folks, and I hope you enjoyed this video of the Rosette Nebula. I enjoyed making it. It is a wonderful target whether you are a beginner or an advanced astrophotographer, so go out there with your telescopes and capture some images. And if you are into astronomy and all things astrophotography, go ahead and subscribe. It doesn't hurt a bit, and it's the very best way for you to be notified each and every time I publish new content, which seems to be every week. And with that, I will see everybody on the next video.